Hi guys. Okay, so Unit 13, still solutions, but this time a little bit more about the properties of solutions, like how they are changed by concentration or other other characteristics or other conditions is the word I'm trying to think of. So another kind of short unit. Math in this one again, so that's kind of good news, but also just some theories and some terms like these. So first off, conductivity. That is one of the properties. Some solutions will conduct a current, some won't. If they contain electrolytes, they would conduct, and these are compounds that can conduct electricity in an aqueous solution, so something dissolved in water, or even in the molten state. Salt is an electrolyte. Non-electrolytes, these are compounds that do not conduct electricity in an aqueous solution or in the molten state. Sugar is a non-electrolyte. Weak electrolytes, this is when only a fraction of the solute will actually carry the current, only exist, a fraction will exist as charged particles. And so they'll carry a current, but typically it is weak. So a lot of times they'll test this with like a light bulb or, some kind of little conductivity tester. And, if it's a really strong electrolyte, the light bulb will be really bright. If it's a weak electrolyte, it will be pretty dim. And so that's where those two come from. The main thing with these solutions is that to conduct a current, they have to contain ions, cations and anions, something positively charged and something negatively charged. Okay, so these particles, the number of ions in solution, we're kind of leading up to some of the math problems, so just kind of bear with me on this. But when you add certain substances to water, some of them will dissociate or break down into their individual ions. This only happens if you're dealing with an ionic compound. So a metal and a nonmetal, something from the left side of the periodic table and something from the right side. And so, for example, salt, NaCl, sodium chloride, it dissociates in water, and it produces two ions, this positive sodium ion and this negative chlorine ion. And just kind of as a side note, and again, we'll talk about this in a minute, polyatomic ions, so like the ones that you wrote on your periodic table, the ones that I have up above the smart board, those, when they break down or when they dissociate as part of a compound that they are in, they would count as one particle. So like for instance, OH, hydroxide, doesn't dissociate. It stays as that ion. That is one ion. Okay, so just for practice, how many particles would we get? So if we have CaCl2, it is a metal nonmetal. It breaks down into one Ca and two Cl, so you would have 3 total particles. MgSO4, there's one of those polyatomics, the SO4. So you would have one Mg and one SO4, and that would give you 2. The next compound, C12H22O11, that's glucose, a sugar molecule typically. It is a nonpolar molecule. You don't have metal, nonmetal. You just have a bunch of nonmetals in there. It doesn't break down at all. It would be one particle. And then the last one, aluminum nitrate. You have one Al and 3 nitrates. That will give you 4 ions. Okay, and like I said, the reason I need you to know that is coming. Okay, so now the really big part of this chapter is colligative properties. And colligative properties depend on the concentration of the solution. And so they, you have to know the concentration, or you have to be able to figure out the concentration to determine how these colligative properties, what they do, increase, decrease, that kind of thing. Doesn't matter what the chemical is. And there are 3 main colligative properties: vapor pressure lowering, boiling point elevation, and freezing point depression. Vapor pressure lowering, I just want you to know the concept, but for the boiling point and for the freezing point, that's where we get to do some math. Okay, so first off, vapor pressure lowering. A solution that has a non-volatile solute always has lower vapor pressure than a pure solvent, or excuse me, a pure solute. Okay, so this non-volatile solute. Non-volatile means that it won't, well, I can't write today, won't evaporate. So I'm struggling with my pen. So that means something like salt, for instance. It will not evaporate, and it will actually keep that pure water, or whatever it is, from evaporating as quickly as it would if it were just pure. So salt water versus pure water, the salt water will evaporate more slowly than the pure water. Okay. Now, boiling point elevation, here's where our first math formula comes in. Adding a non-volatile solute, like salt, raises the boiling point of the solution as compared to the pure solvent's boiling point. So the formula for this is delta TB equals KV times M times I. So the delta TB, that is the change in the boiling point temperature. How much is it going to change by? KB is a constant. I will always give you that constant. You don't have to memorize them. You don't have to, I'm not going to give you any weird charts. I'll just give it to you. M in this case is molality. And remember that molality, little m, is moles over kilograms. Okay, so you'll either be given that, or you'll be given the information to be able to calculate that to plug into your formula. And then I is the number of ions produced. That's why we started with figuring out how many I's are in things. Then that second formula down there, the new boiling point is the original boiling point. So if we're talking about water, water boils at 100 degrees, so the original boiling point would be 100 plus whatever this change is that we calculated. Okay, so yay, it's an example. So question is, what is the boiling point elevation and the new boiling point of a solution that contains 1.2 moles of NaCl in 800 grams of water? Okay, so first thing we need to find boiling point elevation is delta TB, and that is KB times M times I. All right, so KB, like I told you, it is just given. So KB is 0.512 degrees over molality. And then molality, where we just said it is moles over kilograms. So I'm going to plug it in like that. So here's moles. And then I have 800 grams of water, and 800 grams of water is 0.8 kilograms. So here's moles, and here's kilograms. And then for the I, you have to look at the compound that we're talking about, the solute. In this case, we're talking about NaCl. NaCl breaks into two ions, an Na and a Cl, so our I is 2. Okay, so when you work all of this out, you will get somewhere around, let me look at my little notes here, 1.536, and this is in degrees Celsius. This little m cancels both of those things out, so you get degrees Celsius. So what it is saying is that it changes the boiling point of water by that much. So that's boiling point elevation, so that's this first thing. Then to find the new boiling point, so new BP, that is where we take the original BP plus our delta TB that we just calculated. So if we're talking about water, then we have 100 degrees for the original for pure water plus 1.536. So when I add that much salt to that much water, I would change the boiling point of that water by about 1.5 degrees. Okay, so not super duper drastic, but it may be enough to change things. You know, people say like you add salt to your water before you boil pasta and helps it cook faster. That's because it's cooking at a little bit higher temperature. Some people say they just put the salt in to make it taste better. I really don't know, but it is enough of a change that it can be measurable and can kind of change, like cooking times, for example. Okay, so now freezing point depression. Adding a non-volatile solute lowers the freezing point of the solution as compared to the pure solvent's freezing point. So again, same basic formula. Delta TF equals KF times M times I. You have the KF is the constant, little m is the molality, and I is the ion, so just the same. But the one thing that is different is you will subtract. So it will be the original freezing point minus the change. All right, so now, oh, look at that, an example. So what is the freezing point depression and new freezing point of a solution that contains this? Okay, so delta TF should look familiar because we just did this exact same problem. And I've got KF times M times I. So KF is 1.86. Our M again is 1.2 moles over 0.8 kilograms. And then we're dealing with salt still, so it is 2. So when you work that all out, you get 5.58 degrees C. And so then to find the new freezing point, it is original minus the delta TF. So pure water freezes at 0 degrees. So 0 minus 5 gives you negative 5.6 degrees. So it is going to lower the freezing point. Look, if you've made homemade ice cream, that's why you put like rock salt in your ice and kind of then put the canister down in it and spin it and spin it. So it gets actually colder than freezing, and so it will work faster. It's the reason that they put down salt on, or they used to, they don't so much anymore, but they put down salt on the roads when it gets icy because it lowers the freezing point. Usually just enough to make the ice kind of slushy so you don't have as many sliding cars. So anyway, so it is a calculated number that you can get using that formula. Okay, so next with solution, solubility curves. This graph, which I know looks kind of crazy, it gives information about the solubility, which is over here, grams of solute per 100 grams of water. Don't worry about too much about that. Versus the temperature. So most things, as you can see from that graph, as you increase the temperature, the solute, you can dissolve more stuff in there. Very few do the opposite, but this one obviously goes down. So as it warms up, it gets less soluble. Some of them don't change much at all, like this NaCl is a fairly flat line, but some you have really, really big increases. So solubility curves are just basically graphs to read. It's one of those things that you might see on the ACT. So we'll do some stuff with reading those, but it is again one of those properties. Okay, so now predicting solubility. When you're dealing with chemical reaction, particularly double replacement reactions, you will want to be able to predict the solubility or insolubility of products. And there are different ways to do it. I have a table on this slide, and I'll give you another kind of a chart to use that basically tells you when you mix these two ions, are they going to form a solid, like a precipitate in the reaction, or it will look like nothing happens because they stay soluble. So I put this chart on here. It's not the one I typically use, but I put it on there just so you could see what one looked like. But when you're looking like this practice over here, sodium hydroxide, you would find the sodium ion. Oh, thank goodness I have my glasses on. You would find the sodium ion, which is right here, this column, and then you want to see what happens when you mix it or when you form the compound with hydroxide, and it is soluble. When you are putting this or labeling this in an equation, that would be AQ. It forms or it dissolves in water. It is soluble. Calcium sulfate, here's calcium, and then sulfate is, let's see, right down here, it says slightly soluble, so it's still going to dissolve. That one typically you would probably put AQ. But for some of them, they do not dissolve. And so something like, here's lead, and here is phosphate down here. So when they meet over here, then you have this insoluble, that would form a solid. So you would label it with an S if you were writing out the equation, which you will do when you're looking at reactions in aqueous solutions. So when you write it out, it's just a typical, this first reaction, just a typical double replacement reaction. You just kind of say what happens. So silver nitrate and sodium chloride. So they're both, you basically look like you're pouring two clear liquids together. When they mix, it will be clear liquid, but you will also have a solid that is formed, and it will look kind of like flakes, and they kind of start to settle to the bottom, and that is that silver chloride. And you can determine which it is by using the chart from the page before. These are a lot of times written out in more detail, and you can write out what is called the complete ionic equation, and that is where you take everything that is aqueous and you break it down into its ions, because that's what it's actually doing. So the silver nitrate breaks down into the silver ion and the nitrate. The sodium chloride breaks down into the sodium and the chlorine. And then this nitrate, oh, wrong arrow. Then this nitrate, hang on, I'm struggling a little bit. Nitrate and sodium and nitrate, my goodness, and they all break down. So you're showing all of the ions. Notice though that the solid stays a solid, it doesn't break apart. That's why you can see it. And that's the complete ionic equation. And then sometimes you will be asked to write the net ionic equation. And in the net ionic equation, the only things that are important are the things that form the solid. And so you would take the ions from the solid that form the solid and show that they end up together as one of your products. The things that aren't in the solid are typically called spectator ions because they're not doing anything. They're like, you know, the spectators at like a sporting event. They're just spectating. And so it is one of the ways that they look through and kind of see what is happening individually with the ions. Okay. So that is Unit 13. Please, as always, ask me questions if you've got them, and I will see you in class.